All right, so today we're going to look at section 11.5. There are two parts to induction. We're just going to look at the first part. Okay, we're not going to do the second part. So what we're technically doing would be considered weak induction versus the next part of this would have been strong induction. So induction is a way to prove certain things. You want to think of induction as it's like a tool. Right? You don't use it for everything. You use it for certain things. Some things that you would definitely prove using induction, if you have a formula that predicts the terms in a sequence. And you say, you know what, I think this is the formula. And I can show you the formula works for like the first number, the second number, the third number, the fourth number, the fifth number. But you can't show me every number because the sequences go on forever. Well, induction can prove that your formula always works. What else does it work for? Works well for a series too. So if you're adding up a bunch of numbers and you say, you know what, I think I've got a formula. Okay, we can prove that your formula is right using induction. Okay. If you were doing something like trying to prove two triangles congruent, you don't do that with induction. That's a statement reason kind of proof where you do side, 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 or side angle side, stuff like that. That's totally different kind of proof. So the idea with induction is you have to already have an idea of what you think you're trying to prove. Induction doesn't help you figure out a formula. Like if you've got a sequence of numbers and you don't know what the formula is to predict the next one, well, induction's not going to help you find it. Induction is used when, okay, I think I know what the formula is. I'm just not sure if it's right forever. Okay? You can prove that it's true with induction. Okay, but it's not going to help you figure out the formula if you don't know what it is. So any questions on that so far? Okay. So here's a very typical problem that you could prove with induction. You're adding up, this is a series, so you're adding up the first n integers, and I think this is a formula we had last week. It's when you add up, is it one we had last week? I'm not sure. I think we did. It's when you add up the first n perfect squares. Now, if you didn't know the formula on the right, again, induction wouldn't help you figure it out. You would say, all right, you either looked up this formula somewhere, or maybe you remembered it from your notes from last week. But now we could prove that this formula always works, no matter how high you want to go. Okay? So that would be an induction problem involving a series. Okay, I think we're going to look at 3 induction problems, maybe 1 or 2 with a series, and then 1 with a sequence, or 1 or 2, however it works out. All right, let me, okay, so let's look at this. So I'm going to make up this set of numbers, okay? The name of it is going to be called S. And ultimately what I want you to do is tell me what numbers are in my set. Okay? And I'm going to tell you a couple facts about this set. First thing I'm going to tell you is that the number 1 is in the set. The next thing I'm going to tell you is that if you know a number that's in the set, then I'm telling you that k plus 1 is also in the set. So based on these 2 facts, you should be able to tell me what numbers are in my set. Anyone think they know what numbers are in the set here? Yeah. Yep, so that's given. 1 is an element of the set. But that second fact, that's what's getting you to start to think like inductively. What else is in the set besides 1? Yeah? 2? How come?
No,
Emily?
because you just add 1, so like you plug in 1 for k.
Yeah. So, okay, we know 1 is in the set. So if 1 is in the set, then 1 plus 1 is in the set. So that means that 2 is in the set. But what does that mean? 3 is in the set. If 2 is in the set, then 2 plus 1 is in the set, or 3. But if 3 is in the set, what does that mean? 4 is in the set, 5 is in the set, 6. So basically, as long as you know that 1, you have a starting point, right? That number is in the set. And then what you're saying is the 1 after it is always in the set. So that's where the domino kind of idea is coming in. If you knock over the first one, as long as you can prove it hits the second one, then the second one's going to get knocked over too. And if you can prove that the second one is going to hit the third one, then the third one gets knocked over. So that's kind of another way to think about induction, right? And that'll make more sense when we do an inductive proof. So what numbers are in the set? Basically, it's all positive integers. All positive integers. So there's 4 steps to an inductive proof. Okay, let me just show you a kind of an outline of what the 4 steps are. The 4 steps are, first you have to show that the formula at least works for what we call a base case. Right? You got a formula, you think it works? Okay, prove to me it works at least once. How do you prove that? Plug in specific numbers and show me. So that's very numerical. Okay, so that's called your base case. Once you know that it works for that, you can assume that it's always going to work for that base case. All right? So we can assume that it's always going to work for that. Then the inductive part is to show that it works for the one after the base case. If you can show that it works for the one after it, like if it works for 2, well now you're saying, okay, it works for 2. But we know it works for the one after it, so that means it works for 3. But then if it works for the one after it, it works for 4. It works for 5. It works forever. Right? So this is the inductive step. And then the last step of any inductive proof is to basically write down the original problem. Write down, we have shown, and that, what I put right there, that's the original question. Okay, so those are the 4 steps to an inductive proof. Base case, the assumed step, the inductive step, and then just kind of the last step, which is saying, all right, we've proven what we wanted to prove. So the last step is kind of, that step is simple.
Can you go down there?
Yeah, I mean, we're gonna go through this whole proof. So it'll, it's gonna probably be on the board for like 10 or 15 minutes as we go through it. Yeah, but that's the template for every inductive proof that you do. 4 steps. All right. So you've got to have a starting point. Okay? Like I told you, 1 was in my set. That's called your base case. You've got to prove to me that it works, that the formula you're thinking of at least works for one specific case. And that's called the base case. Usually, in fact, for all the problems we do today, the base case is going to be when n equals 1. So if it was a formula for adding up integers, you would be showing me that the formula works if you add up the first 1 integers. If it was a formula that predicted terms in a sequence, you would show me that the formula correctly predicts the first term of the sequence. You'll be given the first term, you'll be given the formula. Show me that the formula works for the first term. I mean, you could show the second term too, but that doesn't really make sense because when you're knocking over dominoes, you don't have to knock over the first 2. You just have to hit the first one, it'll hit the second one for you. And you can hit both at the same time if you want, but you don't need to do that. Okay, so that's your first step, base case. After we've proven that the formula works for what we call the base case, we can assume that the easiest way to think about it is technically you can assume that it would work for any specific value. Right? But that's kind of like proving, okay, I could prove it works for 2, I could prove it works for 3, I could prove it works for 4, I could prove it works for 5. You can't really do a proof that way. You can't prove every single possible number. Right. So think of the assume step is it could work for any specific value you could think of, and you could check it if you want, but you at least checked it for when n equals 1. So you know that it works for that one. Okay, that's the important thing. Okay, so assume that it works for any specific value. If you want to keep it simple in your head, just say, okay, I know it works for at least the value that I just checked in the first step. I checked it and it worked. Just think of it that way. Okay. Now, this is the inductive step. You want to show that it's going to work for the one after the one you picked. And I don't mean show that it works for the one after by saying, okay, I plugged in 1 and it worked. Now I'll plug in 2 and it works. No, you haven't really shown that it works for the one after. You have to use this kind of general idea, k plus 1. Okay, that's the one after. Okay. Trying to show that it works for like every number individually would kind of be like taking a domino and just flicking it out of the way. Okay, you got rid of it, but you didn't knock it into the next one. And yeah, technically you could just flick as many of them as you want out of the way, but it'd be a lot easier if you just prove the first one hits the second one, then they're all going to knock each other over, rather than just flicking them out one at a time. And if there's an infinite amount of dominoes, you can't hit everyone out one at a time. Okay? You'll be there a little while. All right? All right, so inductive proof, it's really the kind of thing you got to go through it a few times. So I think we just have 3 examples, and that's it. So we're just going to look at some examples. Now, this one, they've given you an expression on the left, and they've given you a formula on the right. Okay, I know that's a formula we looked at last week. It's the formula for the sum of the first n integers. Okay, last week I just said that's the formula, it just works, don't worry about it. Now we're going to prove that it actually works. So the first step, and this is your base case, show that the formula works for n equals 1. So let's start with the left-hand side. If you add up, and for the base case, you just let n equal 1. So just look at the first number. If you add up the first n terms on the left-hand side, what do you get? If you add up the first 1 terms on the left-hand side, yep, 1. You just get 1. Now, let's use the formula, plug in n equals 1, and see if the formula correctly predicted what we should have gotten. So on the right-hand side, using the formula to add up the first 1 terms, you'd have 1 times 1 plus 1 over 2. Okay. So what do you get if you simplify the right-hand side formula? 1. So what we've done is we've just shown that yes, the formula did work, at least for when n equals 1. Okay. Does it work when n equals 2 or n equals 3? I don't know. So what I've done right now is I basically hit the domino out of the way. But what I'd rather do is hit that domino into the next domino. And then I've done the proof. Any questions on the base case? That's usually pretty easy. All right. So now we get to the assume step. So we can assume that our formula would work for any particular value of k. Now we only checked it for k equals 1. Could I check it for k equals 3 if I wanted? Sure. I'll just do it quick, but I'm not going to do it again. If I add up the first 3, I get 6. If I plug in 3 over here, 3 plus 1 is 4. 4 times 3 is 12. 12 divided by 2 is 6. Okay, so the formula works if you do the first 3. I could check it for the first 3. 5, 6, 12. You could check it for the first 1,000 if I really wanted to. Okay? So I can assume that this formula would work for any single specific value. But when you have an infinite amount of values to check, you can't flick those dominoes out, even if you say, well, I'll just keep flicking them out forever. Well, if there's infinitely many, you'd never finish. So we want to knock one domino into the next. So now we're going to write down our assume step. We're going to assume that 1 is 2 is 3 plus at least up to k. Okay, we don't know if it works past k. Maybe you get to the first 600 terms and all of a sudden the formula doesn't work anymore. Maybe 601 messes it up. If it did, then our proof isn't going to work. If that formula really is the real formula, then our proof will work. Okay, so we'll know very quickly whether that formula is right or not. And it's k times k plus 1 over 2. Okay, questions on that step? So think of k as like maybe I checked up to the 5th term, and I know it works there, maybe the 6th or the 7th, but it works up to some point. But my goal is to show that it would work beyond that point, okay? And I can't check manually, because if you said, well, okay, it works for 3,000, I'll just check beyond that point. I'll check 3,001. And what about 3,002? You're going to check that one, 3,003. You can't keep checking them all by hand. Okay? So we can assume that maybe it works up to some point. All right, so now, what we want to show. Sometimes I write we need to show, sometimes you'll see me write this, like WTS, I want to show that the formula works for k plus 1. Okay, so this is what we want to show. 1 is 2 is 3 plus k, which I'm good up to there. I know I've got a formula that works to k. I want to prove that if I did this, if I put the next term in, it would also work. So here's where the induction is kind of coming in. I'm saying my formula works up to a certain value. I want to prove that it would work if I do the next one after that. And then you'll have that domino effect if it works for the one after. Okay? So that would be, basically we're just changing k to k plus 1. So the next term after this one would be k plus 1. And the one after k plus 1 is k plus 2 over 2. Any questions how I got what's on the right-hand side here from what I had circled up there? So all I basically did is say, okay, if this is the formula up to k, then the formula for k plus 1 is just changing all your k's to k plus 1's. So technically I have k plus 1 here, k plus 1 plus 1 here, which I just wrote as k plus 2. Okay, any questions on that? Okay. So if we made this assumed step correct, then this formula, this is new, this is something we just based off of what I have here, it should work. Okay? So let's see. For this part, we have a formula that we already assumed worked correctly. If you add up all the numbers from 1 to k, based on our assumed step, what's the formula for that? This is going to be like substitution here. What are we assuming that all the numbers from 1 to k add up to? Yeah.
Isn't it k times k plus 1
Right. We're assuming that everything here adds up to k times k plus 1 over 2. If we're wrong in that assumption, then this proof is going to fall apart very quickly. If we're right, then we have the right one. So that's up to k, but now we're adding one more term. And based on our formula, when we add one more term, I should be able to just change all the k's to k plus 1s, and the formula should work. Okay. So that's the question. Does this work? So, how could I see if what's on the left and what's on the right are the same? What would I have to do? Yeah.
Put something in for k.
Well, you could try it, but that would only prove that, say you plug in 2 for k, and you get the same number on the left and on the right. Okay, it worked for 2. But I have to show that what's on the left is always the same as what's on the right, no matter what you plug in for k. 2, 12, anything. So how would I go from here? I mean, if I showed that to somebody in, like, I don't know, first grade, and I said, does what you see on the left, is that exactly the same as what you see on the right? They'd say no. They don't look the same. I mean, one has, you know, a fraction here with a 2, but this part doesn't have a fraction. This is like one big fraction. They look different, but they could be the same. How would you figure out if they're the same? Yeah.
On the left-hand side, you have to add them together.
Yeah, we could let's add these together. We can find a common denominator, add everything together, FOIL everything out, and simplify. We can actually do a little bit in the top here first. What can I distribute in the top there? Nate?
Okay.
Yeah, and if you distribute that, what do you get?
K squared and k.
Yep, so what I'm going to do is I'm going to write it like this. 1/2 k squared plus 1/2 k. Because I'm dividing each one of them by 2. Plus k plus 1. So I'll come back to that and combine like terms in a little bit. How about on the right-hand side? What do I have to do to take care of that? Yeah. Yep, we got to FOIL it. And remember, everything is going to be divided by 2. So I'm going to get k squared. I'm going to get 2k plus 1k. So that's 3k. Oops. So that's going to be 3k. And then 1 times 2 is plus 2. We just said all of that's divided by 2. So 1/2 k squared, 3/2 k. And that's really going to end up just being a 1. Okay. So let's finish combining like terms here. Anything to combine with the 1/2 k squared? No. How about 1/2 k and 1k? What does that give me? 1/2 k, or if you write it as a fraction, plus 1. So that's the left. And now look at the right. 1/2 k squared plus 3/2 k plus 1. So what you've just shown is that you made a prediction saying, all right, we know the formula worked up to k. What would happen if you went to the one after? So change all your k's to k plus 1s. So I added a k plus 1 on the left, and I changed all the k's to k plus 1s on the right. And if my assumption step here was correct, then by just doing what I said, it should work. And it did. Okay, so we simplified it, got exactly the same expression on the left and on the right. So now you've just proved that if it works up to k, that's going to hit the next one and knock that over. And that's going to hit the next one and knock that over. So now it will work forever. It works for every possible value. And the last step is just to write what you have proven. So the what you've shown step is basically just the question written down again. you have shown that your formula is true. So we use n usually when you're trying to prove like the end result. We usually use k, and you can use different letters, but we usually use k when we're like in the middle 2 steps. Think of k as like a smaller value than n. Like, okay, you've shown that it worked. Maybe you checked it up to 1,000 and it worked. Now you're going to show that it works for 1,001, which will then prove it works for 1,002. All right. So think of n as like, okay, that's not just up to 1,000. That's everything. Okay, it works for all values. So any questions on that? That's an inductive proof. So it doesn't really involve like statement reason. It's more algebra. It's pretty much how it goes. All right. So let's try this one. So this is a formula that says if you add up the first n odd numbers, it will add up to n squared. So like if you added up the first 5 odd numbers, it should add up to 25. If you add up the first 9 odd numbers, it should be 81. Still not too bad, because they gave me a formula. In the next example, I'm just going to give you guys a pattern, and you're going to have to find this part of the formula yourself. And then from there, we're going to prove whether what you found is right or wrong. I think that's example 3. Okay, so first thing we want to do is our base case. Okay, so this is the base case. We're going to show that the formula works at least when n equals 1. So, start with your left-hand side. If you add up the first n numbers on the left, in this case 1, so just add up the first 1 numbers on the left, what do you get? 1. And it's not always 1, it's just that's just how this one is. Now let's see if the formula on the right predicts that correct. If you plug in 1 and square it, what do you get? 1. So yes, the formula correctly predicted the result, at least when n equals 1. Now we could do it. Let's add up the first 3. What's 5 plus 3 plus 1? 9. And I added up the first 3. What's 3 squared? 9. So yeah, okay, it works for the first 1, it works for the first 2, it works for the first 3. We can check first 4, first 5, first 6. Fine, let's just assume that it works for k. Okay. Maybe it works for the first 50. But maybe there's a problem when you get to 51. All of a sudden the formula breaks down. Well, we're going to prove whether that happens or not right now. So assume that your formula would work up to any particular value you want to check. Remember, we can't just sit here checking all of them by hand. So now the goal is going to be, okay, it works to k. Let's prove it works for the one after. Right? And then you're good. So assume that it works for k. So the formula would work for 1 plus 3 plus 5 plus up to 2k minus 1. Now if you wonder why 2k minus 1, because that's how you write an odd number. If you take any number, double it, and minus 1. Anything doubled minus 1 is always odd, because anything doubled is even. And then if you offset it by 1, it's odd. So that's why it's 2k minus 1. Okay, so any questions on the assume step? Okay, so we're assuming that the formula would work up to, maybe you tried it up to when k was 10. Right? Doesn't matter. It works up to some point. Now let's prove that it works after that point. All right, so we have 1 plus 3 plus 5 plus 7 plus 9, plus 11, plus 30. I mean, you can write as many as you want, but eventually you're going to get to the kth term. And now I want to put in the term after that. So if I'm at the kth term, how do you write the term after? It would be the what term? Yep. It'd be the k plus 1 term. So this is the first term, second term, third term, fourth term, kth term. The k plus 1th term. So what do? Change k to k plus 1. 2k plus 1 minus 1. That would be the term after that. Change k to k plus 1. And I can do that out. It's going to be 2k plus 2 minus 1, or 2k plus 1. That's what it's going to end up being. I'll do that out later, but not yet. So now, if our assumed step is correct, you should be able to add a k plus 1 on the left, just like we did, and you should be able to change k to k plus 1 on the right, and the formula should still work. Okay, it should work all the time. So that's what you want to show. If you add a k plus 1, if you add the next term on the left, you should be able to change the k to k plus 1, and it should work on the right. If it doesn't, then that means your formula doesn't work for the next term, and that's a problem. Okay. So the next part in your what you need to show or what you want to show is to do substitution. We know that everything from here up to here, we're assuming we have a formula to handle that part right there. What are we assuming that everything in that bracket adds up to? How much? And careful, n is not in our assumed step. N is kind of reserved for the final answer.
K squared.
K squared. We're assuming everything here adds up to k squared. And if you're saying, well, what if it doesn't? What if we assume wrong? Then the proof's not going to work. And then that means this step was wrong. So we're assuming everything up to right here adds up to k squared. But I'm interested, what happens if you add the next one after that? 2k plus 1 minus 1. And according to my formula, the result should be k plus 1 squared. So let's do out the left, do out the right. If they come out the same, then that means our assumed step was correct, and we proved that it not only works for that, but it always works for the one after, and that's induction. Okay, so let's see what happens. We have not shown yet, but we will. Okay, so this is going to be k squared. What did I say 2 times k plus 1 minus 1 comes out to? Okay, so that's the left. And the question is, when you FOIL out the right and do k plus 1 times k plus 1, what do you get?
2k.
Just 2k?
If you add 1, wait, what?
You're going to do this all out right here?
Oh, it's not just 2k, like you want the whole...
Yeah, because if it was just 2k, then the left and the right wouldn't match, and then we have a problem.
k squared 2k plus, I think 1.
K squared plus what?
Plus 2k.
Oh, 2k, okay.
Yeah.
Yep,
I think the final curve is just 1.
plus 1, yep. So when you FOIL out what's on the right, you get k squared plus 2k plus 1. From our assumption step, we get k squared plus 2k plus 1. That means that what we assumed was true. So this formula does work. So we have proven, and now you can just write the original problem. And you can write, we've proven, we've shown, we've anything like that. Okay, but the way I grade a problem like this, you'll have one of these on the test. Okay, one inductive question. The rest of the test is going to be stuff we do tomorrow. So I might make each part here, they'll be worth the same. Maybe each part's worth 5 points. So this would be like a 20-point question. About 4 little parts that you have to get right. Questions on that? Right, so we did a proof involving a series. We did another proof involving a series. Let's do a proof involving a sequence. So this is going to be a problem where I give you a recursive formula. I want you to find the explicit formula and then prove to me that your formula would work all the time. You know, don't just say, well, I checked it. It worked for the first one, the second one, the third one, the fourth one, and the fifth one. What about the sixth one? Did you check that one? Okay, I'll check it. All right, what about the seventh one? Eighth one, ninth? So the point is, you can't check it forever. So you got to do a proof. So they gave us the formula, but let's just practice finding it, because you might have one where you have to figure out the formula yourself. That's what last week's test was on. So this is an arithmetic sequence. If I don't remember the formulas to figure it out, what I do is just list a few terms. What's the first term in this sequence? 4. And what's the next term? 7. Okay, and let's just do a couple more. Third one? 10. And how about the fourth one? 13. So does anybody see the pattern with what you do to the term number to get the term itself? Yep.
Times by 3 and 1.
Yeah, that's the pattern. Now, that's just what you've observed, at least from the first 4. Maybe that doesn't work when you get to the 5th or 6th term. That's what we're going to prove. So 3n plus 1. Okay. That, well, I'm not going to put a box around it, but that's what we want to prove. Okay. So somebody tell me, what's always the first step in an inductive proof? What do you have to do first?
Show the formula.
Right. Let's prove that the formula that Robin thinks is right. Let's prove that that actually works, at least to predict the first term. And then you can check the second term, the third term. You can check as many as you want, but you only have to check one base case. So that's what I have right here. This is your base case. It's like the starting point for the inductive proof. Okay. So show the formula works for n equals 1. That usually involves writing down what you have on the left-hand side and a right-hand side. The left-hand side is usually given. The right-hand side is some formula you're going to calculate a value. So, what is the first term in my sequence? 4. Okay? And that's from the left-hand side, given. Okay? That's why that's like that. Now, to show that the base case works, I'm going to use the formula that we think we need to use, 3n plus 1, and what number am I going to plug in? I'm going to plug in 1. So right-hand side, 3 times 1 plus 1, yep, comes out to 4. So you have shown that the formula correctly predicted the first term. We could show that it correctly predicts the second term. 3 times 2 plus 1 is 7. The fourth term, 3 times 4 is 12, plus 1 is 13. The fifth term, the sixth. Okay, let's just assume that it works up to k. Right? So now that's my next step. Assume that the formula works for a particular value of k. So now we're going to basically write down the original problem. Well, They didn't actually give it to us here because we had to figure it out. So let's do it like this. All right. So we're going to assume that the kth term would be given by this formula. And that should be under the assume step. Sorry. Now, you're not seeing a plus here, like the dot, dot, dot. We're not doing that here because the formula is just finding a sequence. We're not actually adding anything up in this problem. But the proof is still the same idea. So I'm going to assume that my formula would correctly predict the kth value. But I want to show that my formula would correctly predict the what value. What am I interested in to make the induction happen? It works for the kth term. I want to show that. Yeah. I want to show that it works for the one after, and then if it goes from there. Okay, so we need to show that the formula works for k plus 1. Okay, so here is what we want to show. A sub k plus 1 would equal that. All I did was change k to k plus 1. Any questions on that? All right, so now let's go back up. So I haven't really used this idea in the proof yet anywhere. I know what I just circled is true because they gave me that. They said that to get the nth term, just take the term before it and add 3. Okay, so that's another way to think about the k plus 1 term. I think this way is better because this is explicit. Right? If you want to know the k plus 1 term, plug in a number for k and there you go. Doing it recursively, you could think about it like this. A sub k plus 1 equals 3 plus the term before. So what's the term before k plus 1? K, right. So technically, this should be this. To get the k plus 1 term, you should be able to back up, take the term before it, and add 3. Now doing that here, and doing this here, should come out the same. That's the goal. If we use, this is the formula Robin gave us, we're just plugged in k plus 1 into it. If doing that gives us the same result as taking the previous term and adding 3, then we know the formula works. All right, so we have to go up and see from our assume step, do we have a formula for a sub k? Yes, we do. We're assuming that the kth term is given by 3k plus 1. That's the kth term. If I add 3 to the kth term, I should get the k plus 1th term, which we already have a formula for. Let's see if they come out the same. What's 3k plus 1 plus 3? Yep. Yep. So I get, that's calculating the k plus 1th term recursively. I don't think there's any in there. explicit. So I know that that's correct. I just took the term before it and I added 3. Now let's use the formula and see if we get the same result. If I distribute out the 3, I get 3k plus 3 plus 1. 3 plus 1 gives me 4. Now, doing it this way, I didn't use the previous term at all. I just took the formula Robin gave me, I plugged in k plus 1, and hoped that I got the next term. And I did. Plugging k plus 1 in, gave me 3k plus 4. Adding 3 to the term before it, gave me exactly the same result. So this was doing it explicitly. So we've shown that yes, the formula that we were given, or that we figured out, does correctly predict the next term based on what it should be if you did it recursively. It worked perfect. So a little bit different, not a lot different, but you're still showing that two things are the same. Okay. And then your last step, just write what you have proven. So I left a lot of space, but we didn't need all that. Right. So we have shown that this explicit formula gives you the exact same result as if you did it recursively. Okay. So any questions on that? So that's the idea of induction. It's not too bad, but it is kind of one of those things you just have to practice a little, wrap your head around. And then tomorrow's lesson is a lot more concrete. It's very like, here's 3 color pens. Tell me how many different ways I could pick 2 out of 3. Right? Things like that. So very, very concrete versus this is much more abstract. All right, on 624, homework is 1 through 7 and 13. So you got about 25 minutes. So if you need to take a picture of the book, you can. If you flip through it and you don't understand something the book says, just let me know and I'll explain it to you.